Hi everyone, myself Dr. S. Kannappan. I present a course called Digital Signal Processing, which is very much essential nowadays. All the systems are digital in nature, so it is very essential to know about the digital signal processing. So in this course, I cover 9 modules. So module 1 is about discrete time signals and systems, the basics about the digital signal processing. Before going to completely discuss about digital signal processing algorithms and the mathematical formulas and mathematical procedures that behind the processing of signals, we should know about the basics behind digital signal processing concepts. So that is discrete time signals and systems. So module 2 is the two specialized transforms for analyzing the signals or systems in frequency domain. So that is discrete Fourier transform and also Z transform. So module 3 covers fast Fourier transform algorithm. It is an efficient algorithm to calculate discrete Fourier transform, which is very much essential in most of the communications systems, in all the digital systems also. And module 4 and module 5, we are going to study about the filters, digital filters and their design. Broadly, the digital filters are two types, IAR filters and FAR filters. So infinite impulse response filter is IAR filter and finite impulse response filter is FAR filter. So these two filters and their design is covered in module 4 and module 5. Module 6 is to realize those two filters in terms of hardware. That is the structure of digital filters. So more particularly, the two categories we are going to discuss, IAR filters and FAR filters and their structures. And module 7 covers multi-rate signal processing. So up to module 6, we always concentrate with single sampling rate only, we assume. And but in practical, any digital system may not work with one sampling rate, but multiple modules may be involved in any system. Those modules may not work with the same sampling rate. One module may work with one sampling rate, another module may work with another sampling rate. So how this multiple sampling rate processing can be combined together, and so we need to have some knowledge about multi-rate signal processing techniques, so that can be integrated in a real-time system. And module 8 and 9, so completely focusing on the processors, so the actual processor which is going to perform all the digital signal processing concepts we have discussed so far, the modules we have introduced. So module 8 is the programming DSP, digital signal processing, the programming part of all the digital signal processing operations. And module 9 is to know about a particular family of processor that can do all the digital signal processing concepts. Now let's move on to module 1. The module 1 is the basic concept, so discrete time signals and systems. The main uh, objective of this course is we should know about the systems, digital systems, which needs some processing of digital signals, because the digital systems can take only digital signals as input and it will produce digital signals as output. So as the system nature is digital, we need to know about the digital signals. But why? So we are confined to discrete time signals only. So let us see that difference between discrete time signal and digital signal in the coming discussion. Because the basic difference between discrete time signal and discrete digital signal, we can say the discrete time signal is having continuous values, but the time is discrete. The signal is measured at discrete instance of time. Whatever the value at that particular instant, the same value will record. It may be integer or fraction, and it is in numerical in nature. It is not completely, the values are not completely digital. But when we move on to digital signal, this the values we measure at discrete instance of time is completely represent digital. So a human cannot process a signal which contains n number of samples and all are represented in binary. So it is not possible to analyze the digital signals manually by a human. So we'll analyze and understand discrete time signals, but the same operation, if it is done by a digital system, if the signals are represented in digital and it is the same algorithm what we are discussing on discrete time signals can be applicable for digital signals also. Only the difference is the values are represented in binary. A system can manipulate all those binary values and it can process the binary values. It can understand, but human can't. So for understanding the operations, the processing techniques, instead of going completely purely digital, we can process discrete time signals. So same processing steps can be used for digital signal also, but it can be done by a system. So that's why it's the basic difference. A human cannot completely understand all the values. He cannot add and subtract. He cannot process so many operations by using digital signals. So discrete time signals can be feasible for a human to understand and then process it further. After deriving the algorithms, it can be applicable for the digital signals also. So this module 1 covers this basic concept. So let's first see the difference between continuous time signal and then discrete time signal. Next we'll discuss with the digital signal, and then sampling process. The basic concept in the discrete time signal is sampling. How we'll achieve discrete time signal from the continuous time signal means sampling, right? So after discussing the idea behind the discrete time signal, that is sampling, let's move on to the various kinds of signals and systems. So the basic signals, that is called elementary signals. The basic signals are very important. These signals are used to form any complex signal. Any complex signal can be represented as a combination of these elementary signals. So it is necessary to know about the properties of elementary signals and how it can be represented. The next topic is signal operations. So all these signals can be used, processed to extract the information. So processing means it involves so many mathematical operations. So what are all the basic mathematical operations that can be done or that can be applied on a signal? Those are all the signal operations. And then we'll move on to system. So in the system, particularly we are going to study about LTI system. We'll see all the types of system. And why we confine to LTA system, that we are going to discuss. And what is the characteristics of LTA system, how we can analyze the system, how we can get the output of the system, those process we can discuss. So in this process of finding the output of an LTA system, the main important operation is convolution, and then uh, followed by a relevant mathematical operation called correlation. Okay. So next we'll see some important property of a system is stability of the system. So the stability concept we'll see. Meanwhile, how to find the response of the system, that also we'll discuss. With this, we can cover the signals and systems before going to enter into digital signal processing. So let's have a glance on what are all the applications of digital signal processing. These are all some regularly day to day life. Uh, we know these kind of uh, machineries we are using for our diagnostic purpose, for medical applications. So if you see this one, first one, hearing aid. So if anyone lost their hearing sense, then a specialized device is used to wear by the person so that he can hear all the sounds, audio. So this contains some kind of signal processing operations. There is amplification, filtering. These are all the signal processing operations. So first, it will capture the signals. The system will capture the signals, and where the in which frequency band the human lost his ear, that frequency band is particularly amplified. That is extracted and it is amplified to a level which cannot harm the person. So which can be a safer level to hear. So that can be achieved. The decision of changing that level is done by a AGC circuit, automatic gain control circuit. So that is also there inside this one. That automatic gain control circuit is, it will do some kind of operation. It will automatically adjust the gain. So that is multiplication of the gain or reduction of the gain. So that is also a signal processing operation. Amplification, increasing the strength of the signal. That is also a signal processing operation. So it contains circuits which can do signal processing operations in the real time. And the next one is electroencephalogram recording system. This electroencephalogram recording system is used to record the brain signals. The electrodes will be placed on the scalp of a person. It will read the signal variations in the generated in the brain. That can be, again, it is used to amplify in a particular frequency band. And the system itself is having some kind of electrical signals that can be removed by using filters, and it only extract the brain signal. So just the frequency band where the natural brain signals lies, in that frequency band only it can amplify, and it is represented on a display. It all contains some digital processing, signal processing. So digital means the system we are using to perform all those operations is digital, because it is having some advantages over the analog amplifiers, analog filters, so analog circuits. So we'll see that also at the summary of this one, the advantages of digital signal processing than the analog signal processing. And the most important one, ECG. So to see the heart rate of a person, we used to take the ECG of a person, and it is analyzed by the duct. So the rate of blood pumping will be decided, will be analyzed by using this ECG signal. Right? So it is also a signal processing concept. It contains, these are all the block diagram for this one. It will take a raw signal and it will remove some kind of noise by using filters, band stop filter. So just it will eliminate 50 Hz filtering. So every electrical device has a 50 Hz frequency uh, from the power supply. So that may cause some kind of unwanted information. If that signal is added in the message signal, it leads to show some additional information. So which may be wrong information, and it is very crucial in diagnosing in the medical domain. So it is very crucial to remove this one. So filters again we are using, and it has some kind of set of filters like high pass filter and low pass filters, so for extracting this, and also uh, blood pressure signal. So if you measure the blood pressure, it is actually around some 15 to it has some significant amplitude in this range below 35 Hz. So if anything, any noise is included in this frequency, so it may indicate that rise of blood pressure. So we need to remove this. So we need some kind of signals, some kind of filters which can accurately remove this very narrow band signals. So, so a lot of applications are there to analyze the real-time signals. So for this purpose, we need specialized devices which can capture the signals and which can process it and provide an accurate information from the message signal. So this is how in the real time we have a lot of applications for the digital signal processing. And before going to discuss about this one, the difference between the continuous time and discrete time signals. So let's discuss some advantages of digital signal processing, then analog signal processing. The main advantages is because of digital systems. So the digital systems are represented in binary. It will take the values in binary. So the values are more accurate than the analog values. And another one is the digital signals can be stored in a digital memory. So it is very cheaper now. So it is another part. Storing is possible, so that a laboratory signal can be stored and it can be analyzed uh, any time, or a real-time signal is captured and that signal is stored, that can be bringing to a laboratory and we can analyze it. And another important process is the system can be reconfigured. So digital signals are highly programmable, but analog signals are not completely programmable. They are highly depends on hardware. If you want to change the system, we can simply change the program and we can run the program, we can update it. So the reprogrammability concept is there, so flexible in system upgradations, uh, configurations. But in analog, it is not possible. We want to change the hardware completely, or with minor changes also. To do a minor change also, we need to change the components. So which may lead some malfunctioning or some kind of disturbance to the system. Flexibility is issue. And then dynamic range. So in the analog electronic systems, the amplitude levels are it is limited to supply voltage, saturation levels only. We cannot generate lakhs and crores of values or output voltages in terms of voltage and current. It is not possible. But in digital, it is possible to represent n number of values because it's a combination of flip-flops. The values are stored in registers. Combination of flip-flops all are arranged to have a high dynamic range. So like this, so many number of so many advantages are there over digital, over analog system, for the uh, having a digital system and doing all those better operations. So now let us move on to the basic concept, the difference between continuous time signal and discrete time signal. So continuous time signal, and uh, before this one, just let's clarify one thing. We are discussing mainly only one-dimensional signals in this study. We are not going to discuss about multiple dimension signal. That means the signal which varies with multiple independent variables. Here the signal varies only with single independent variable. Okay, so we are taking some signal x of t, which varies with time. So the independent variable is mainly time. With respect to time, we are measuring the signals. So if you assume the signal is varying with time, and we'll consider a continuous time signal. A continuous time signal means the signal is varying at all instants of time. So continuously it is varying. That means time may be any value, it may be integer or fraction value. So here the continuous means it refers to all the values, both integer as well as fraction value. So at 0 it has some amplitude, at 0.5 it has some amplitude, at 0.1 second it has some amplitude. So between 0 and 1 we can find infinite number of values. It's continuously varying with time. And also the values can also be continuous. Continuous means all the values, all the possibilities of values. So between 0 and 0.25 we can find n number of values. So continuously, so all the values. So continuous means so fraction as well as integer. So time is continuous as well as amplitude is also continuous. That means orally we can say the signal varies at all instants of time. The signal can be recorded at any instant of time, and the values can be any value, right? But discrete time signal means just will take only particular values only from the signal. Finite number of values we are taking. So let's take this one. It is having hardly 10 samples in the off cycle. In the another off cycle, it is having another 10 samples. So completely, it is having 20 samples only. So 20 values only we are recording. So that means we are taking only at particular instance of time. The signal values are measured at particular instance of time. But here it is uniformly measuring the signals. At uniform intervals, we are measuring the signal. That is called uniform sampling. Sampling means take only finite number of samples, measuring at discrete instance of time. That's why it is discrete time signal. But what about amplitude? So at this instance of time, whatever the amplitude is there, the same amplitude we need to record. The amplitude may be anything. Whatever the amplitude, it may be integer or fraction. So in a discrete time signal, we only discretize the time but not the amplitude. We'll take the amplitude as it is, whatever at a particular instance of time. So that is discrete time signal. So discrete time is discrete, but amplitude is continuous. But whereas if you go to digital, the amplitude is also discrete, because these amplitudes are stored in a digital system. If the amplitudes are in infinite number, how many values, what is the range of these amplitudes means we can't say if it is continuous. We can't predict how many values may be there. That depends on the instant at which, so between 0 and 1 it may be, at some instant it may be 0.26, at another instant maybe 0.51, 0.5001, anything it may be. So we cannot predict. So we cannot exactly decide the register length. So it is required to discretize the amplitude. So we'll discretize the amplitude only to particular levels only. So 0, 0.25, 0.50, 0.75 and 1. So 4 levels were dividing. Okay. So this is called discretizing the amplitude. That operation is called the quantization. So sampling means time domain discretization, and amplitude side discretization is called quantization. Sampling plus quantization, and then the quantized values are integer values. So now we'll round off these values. If it is values between 0.125, the values between 0 and 0. The mid value of 0 to 0.25 is 0.125. The values below 0.125, it can be treated as 0. All the samples, if any sample occurs at this instant which is less than 0.125, it can be considered as 0. If it is greater than 0.125 and less than 0.25, it will be considered as 0.25. So we are rounding off the values to this predefined levels, and these values are represented in binary. Then only we can convert it into digital signal. So digital is, first we are converting the continuous time signal into discrete by simply performing sampling. That means discretizing the signal. From the discrete time signal, we will convert it into digital by performing one more step called quantization, discretizing the amplitude along with encoding. So the values are represented in binary. That is called digital. So this is the basic difference between continuous time signal and discrete time signal. The representation is, and the discrete time signal is represented with x of n, and continuous time signal is represented with x of t. That means x of n ts. So between the gap between two samples, adjacent samples, is ts, sampling period, ts we can say. So at 0 ts, at 1 ts, 2 ts, 3 ts, 4 ts, 5 ts and so on, n ts at integer instant of time. So ts is uniform, n into ts. So ts is uniform, so ts can be hidden. So x of n. X of n means at integer instant of time. What is the time we are considering is sampling interval, ts. Okay. Hope this is clear. Right. So what is sampling? How we need to, what is the condition to take the samples? How many samples we want to take from the signal? That is represented with the sampling theorem and Nyquist theorem. So there is a sampling theorem statement. Any signal, any band limited signal means the signal maximum frequency or bandwidth of the signal is limited, a finite value. The maximum frequency of the signal must be finite or lower value, less value. Why it should be limited, we will discuss after discussing this sampling theorem. The sampling theorem states that if the sampling frequency is greater than or equal to maximum frequency of the signal, then only it is possible to reconstruct the signal. Or we can say in this manner, a band limited signal can be effectively reconstructed from its samples if the sampling frequency is greater than or equal to 2f max, the maximum frequency of the signal. That means the samples we are taking is adequate samples such that the sampling rate 1 by Ts, that means sampling frequency, T is sampling duration, frequency is 1 by Ts. 1 by Ts must be greater than or equal to 2f max. So frequency must be double of the maximum frequency, so that we can effectively reconstruct this original signal from its sample. Otherwise, it is not possible to reconstruct. That means it will be a disturbed signal we can get, that is called the aliasing. For suppose if you take a signal with 5 Hz, this original signal is a 5 Hz signal. This 5 Hz signal is sampled. So like we are taking two different kinds of sample. So it is represented with green color. Okay? So this is one sample, and in the positive cycle we are taking one sample, in the negative cycle taking one sample. This instance. So if we can reconstruct it, if we take a signal in this digital at the instance, if aliasing is occurs if sampling frequency is 1 Hz. 1 Hz means we are taking the samples at 0, at this peak, and at 0 again, and at negative peak, and at 0. If we take this one, we cannot reconstruct back exactly this signal, this sample and this sample and this sample. So it is 1 Hz signal because it is less than twice of 5. It should be greater than the twice of actual signal. It's basic how to take the samples, adequate number of samples. So next we'll go for elementary discrete time signals. So we assume that we have done sampling and we have a complicated signal. The complicated signal, how it can be mathematically represented? It is represented as a combination of basic signals. So what are the basic signals? So let's see the basic signals and then we'll represent any complex signal using these basic signals. So first one is unit impulse sequence del of n, and unit step sequence u of n, and unit ramp sequence r of n, and exponential sequence some a power n into u of n. And sinusoidal signal is also a basic thing what we have discussed in the sampling example. So unit sample sequence means it contains only one sample at origin only. At origin the value is present, and if it is unit impulse or unit sample, it is 1 at origin. If it is not unit just impulse means the amplitude may be any value, some 5 or 6, 7, some a constant. Unit impulse means it is 1 at origin and it is 0 at all values of n. At all n it is 0. Unit step signal means the at all n value the value of the signal is 1, step signal. So from minus infinite to minus 1 the values are zeros. From 0 onwards it starts rise to 1. At all instance of integer values of n, thus it is 1. So it is step signal. So up to 0 it is 0, up to minus 1 it is 0, from minus infinite to minus 1, and from origin it becomes a step, but it is discrete. And ramp signal means it is linear signal. It is a linear signal which varies with time linearly. So when n is equal to 1, the amplitude is also 1. When n is equal to 0, amplitude is 0. From positive 0 to infinite, it is linearly varying. For the negative side, it is 0. If n is equal to 1, it is amplitude 1. If n is equal to 2, the amplitude is 2. If n is equal to 3, the amplitude is 3. If n is equal to 4, amplitude is 4. Likewise, so r of n is equal to n for n greater than or equal to 0. And exponential sequence. What is this exponential sequence? A power n into u of n. Some constant power n into u of n. If constant is greater than 1, then it is exponentially increasing. If constant is less than 1, it is exponentially decreasing samples. And it is multiplied by u of n. U of n is equal to unit value only at the positive instance of time, and it is 0 at the negative instance of time. When a power n is multiplied by unit sequence, 0 multiplied by any value, it will be 0, and only 1 multiplied by any value will get the values at the positive instance of time. So a power n into u of n. Suppose a is equal to 2 power n into u of n. So that means at n is equal to 0, 2 power 0 is 1. At n is equal to 1, the value is 2. At n is equal to 3, n is equal to 2, the value is 4. So 1, 2, 4, 8 in 2 powers. The values are increasing. It is exponentially increased with respect to time. So that is, mod a is less than 1 means it decays. Mod a greater than 1 means it grows. So this is summary of the all these signals. Del of n means unit impulse is equal to 1 at n is equal to 0 only. But u of n unit step is equal to 1 for n greater than or equal to 0. R of n is equal to n into u of n. Okay? So u of n is 1 when it follows n value. A power n into u of n is exponentially decreasing or increasing signal. Oh. So these are all some basic signals. Any signal, for suppose you want to represent a signal like 2 power n into u of n plus u of n minus 1 into a power n u of n, some 3 power n u of n plus some r of n. This is a combination of all those signals can be represented as any signal. Right? So next, operations. To represent it combinedly, we need some operations, addition or subtraction or multiplication of these basics. And also we can shift the signal, fold the signal, scale the signal. So two types of operations we can perform basically on the signals. One is the operations performed on time or independent axis. So with respect to x-axis we will perform, or the operations performed on amplitude of this. Time is not changed, only on amplitude will perform some operations. Okay? So the two main operations that will perform on time is time shifting. So the signal is shifted, amplitude will not be changed, the same signal is going to shifted to another position, another time. And time reversal. Time reversal means the same signal, but it is reversed. Negative side instance of samples will be represented in positive side. Positive side samples are represented in negative side. That is called time reversal. So it is represented with x of minus n, but the time shifting is represented with x of n minus n naught. So if n naught is positive, then it is right shift, or it is also called delay. If n naught is negative, it is called left shift, or it is called advance. So suppose n naught is 1, positive value. N naught is equal to 1 means the value which is going to occur at n has to be occur at 1. So n minus 1 is equal to 0 means n is equal to 1. If it is 0, x of 0, x of n has to be occur at 0, but it is occurring at n is equal to 1. That means delay, the right shift signal. And advance means if n naught is equal to minus 1, n minus 1, n minus of minus 1, if you take n plus 1, take it is 0, assume it is completely things has to be occur at origin, x of 0, but n plus 1, if you take it, if you shifted signal, n is equal to minus 1. Instead of occurring at 0, it has to occur at minus 1. That is advance. So before origin, it has to occur at minus 1, it is advance. So it is called left shift operation. Signal is shifted left side by 1 time. are given in not time, right? And similarly amplitudes operations. So the signal x of n, the n is not changed. If you see, the n is time and amplitude is, this is amplitude, a into x of n. A is amplitude. We are multiplying 1 into x of n. Instead of multiplying with 1, we are multiplying with a into x of. And downsampling means x of m into n. So we are multiplying, so this is a time, so it is a operation on time. It is operation, time reversal is operation on time, time shifting is operation on time. Similarly, time scaling, m is a constant, x of m into n. Take m is equal to 2, x of 2n, right? So that means it will be scaled down by twice. Okay, so instead of expanding the signal, it will be shrink. If n is greater than 1, it will be shrink, down sampling, it is called down. If m is less than 1, it is upsampling. That means signal will be expanded. So this constant, if m is greater than 1, the signal is expanding. If it is less than 1, the signal is, sorry, if m is greater than 1, signal is shrinked. If m is less than 1, signal is expanded. So this is amplitude scaling. We can just multiply a scale, or we can add two signals. That is also amplitude addition of amplitudes. We can multiply two signals, subtract two signals. Okay. So this is about some kind of operations on signals and elementary signals. Now let us see the classification of signals. So what are all the classifications? So classifications, it may be elementary signal or any kind of signal which can be classified into some category. So there are some characteristics for the signal. Based on the characteristics, we can classify into types. So based on the energy or power it contains, we can divide it into energy signal or power signal. Neither energy signal nor power signal also may not comes under any one type. Some kind of signals may be neither energy signal nor power signal. And periodic signals. Some signals are periodic signals or aperiodic signals. And causal and non-causal signal. So causal and non-causal signal is a kind of signal based on the occurrence of samples at the positive instance of time or negative instance of time. Right? So that is let's see this category. And next, just even and odd signals. So even or odd signals, or we can also call symmetric and anti-symmetric signals. So before going to discuss about this one, we'll see this. Right. So what is the classification? How will classify the signals? The total energy of the signal is finite, then it is called energy signal. So the condition is 0 less than or equal to E less than or equal to infinite. That means the total energy should be a finite value. Then it is called energy signal. And power signal, if the average power, we'll calculate power means what is power? Energy per unit time. So E by T. So if the energy is finite, the power may be 0. When T tends to infinite, E is finite, finite by infinite is 0. When it is energy signal, power should be 0. But power signal, average power, energy per unit time. If it is extended to infinite, the energy is finite and for unit time, and if we sum up for infinite time, we'll get infinite. It is infinite. So for example, a sinusoidal signal. The sinusoidal signal, periodic signal, will calculate only one period. That is average power, energy per period. If you calculate the total energy means, total power means, so all adding all the power energies is infinite. So we'll calculate only one period or per unit time the energy, that is called power, average power. If it is finite, the finite values are added for infinite number of times. That means E is equal to infinite. So this difference we should be able to remember. For energy signal, power is 0. For power signal, energy could be infinite. What is the energy? How can we calculate the energy? So energy is nothing but sigma x square of n. Just square of the sum of squares of the six samples. But energy is, sorry, power is energy per unit time. So limit n tends to infinite 1 by 2n plus 1 sigma x square of. So 2n plus 1 means we are calculating over a period minus n to n. So over a period from minus n to n, we are finding the energy. Sigma x square of n over the period minus n to plus n. From minus n to plus n, how many samples are there? 2n plus 1 samples. From minus 1 to minus n, it is n samples. From 1 to plus n samples. At origin 1 sample. So minus n to plus n, we have 2n plus 1 samples. That's why the formula contains by 2n plus 1, energy by 2n plus 1 when n tends to infinite. Similarly, periodic and aperiodic signals. So periodic means the signal repeats after n samples. The same samples repeats after some n samples. That is x of n equal to x of n plus n. It is periodic. So for example is sinusoidal signal. And then causal signal. So x of n is equal to 0 for n less than 0. That means for negative instance of time, value is 0. That means all physical signals are, it starts from present, no past values will consider. So the signal happens from right now, from present to future. The values will be occurring. So only at past instance of time, the value is present means it is a causal signal. It should be completely 0 for negative instance of time. For example, unit step signal is a causal signal. At even and odd signals. The even and odd signal means if you fold the sequence, we'll get the same sequence. X of minus n equal to x of n means is a even signal. The odd signal means x of minus n is equal to minus x of n. It is odd signal or asymmetric signal, we can say. So sinusoidal signals are sine waves are odd signals, cos waves are evens. Because even if you fold the cos signal, reverse the cos signal, we'll get same cos signal only. But if you reverse the sinusoidal signal, we'll get negative at the positive side, positive at the negative side. So it is odd signal. Right. So now let's see the classification of systems. Now we will enter into systems, and in that particularly main important systems we are going to discuss about. So system means a combination of interconnection of components. So some kind of components are interconnected in such a way to achieve a desired output when we apply some kind of input signal. So that is, for a given input, it produces some desired output. So to get the desired output, it needs some internal structure. That components, some kind of compression, it will be connected. We are not worried about the how the connections are there internally. So we'll just want to categorize the system based on its characteristics. Instead of what structure it is having, instead of knowing about the structure, just we should know about what it will do, what operation it will perform with that structure. Based on the operation, we can say its characteristic, right? So based on its characteristics, or we can say its characteristics means transfer function T of will represent like T of. T of. Okay. So the system is represented with T within bracket. That means T of AX1 of n plus BX2. When we apply AX1 of plus B, this signal, what is the system function? T of. It has a function. The independent variable is signal. Input signal we are applying to that function. It produces some output. Okay. That is system. So we'll categorize the system into these five types. One is linear system, time invariant system, causal system, and stable or unstable system, memory system or memoryless system, or we can say static system or dynamic system. This linear and time invariant system means the system is both linear as well as time invariant. That is called LTI system, linear as well as time invariant system. This is a special kind of system. All the physical systems are mostly linear and time invariant systems. That's why we are mostly concentrate on LTI system analysis. Now let's see what is this classification. Linear system means the system is said to be linear if it satisfies superposition principle. What is superposition principle? It has two principles again, additivity and homogeneity. So additivity means if we give two input signals separately, it will produce two separate responses. That means x1 of n, if you apply for the system, it will produce t of x1 of n. If you apply x2, it will produce t of x2. If we apply x1 plus x2 as input, then the output must be equal to t of x1 plus t of x2. That means if you apply input as a combination of multiple inputs, then the output should also be combination of responses of the corresponding individual inputs. That is called additivity principle. What is homogeneity means? Not only addition, if any signal is multiplied by a constant, if the input is multiplied by a constant, then the response should also be multiplied by constant. So T of A x1 is equal to A into T of x1. That is called, it is a combination of both additivity and homogeneity. So this AX1 plus BX2 is a combination of additivity as well as homogeneity. So if you give a signal like a mixture of two signals and the signals are multiplied by constant, means the response should also be multiplied by constant and addition of the two responses. So then if such such systems are called linear system. It is not equal, then it is non-linear system. Right? So for suppose x square of y of n equal to x square of n. It is not a linear system. X square is not a linear operation. So if you give x1 of n, it will generate x1 square. If you give x2 of n, the output is x2 square. If you give x1 plus x2, it will produce x1 plus x2 whole square. If whatever the input will apply, the total input will be squared. Then is it equal to two responses, x1 square plus x2 square? No, x1 plus x2 whole square is not equal to x1 square plus x2 square. So it is non-linear. X square of n is a non-linear system. Similarly, next we'll see time invariance. What is time invariant? So time invariant means even though if you shift the signal, the response should also be shifted. So x of n minus k is equal to y of, if you give x of n as input, it will generate y of n. If you give x of n minus k as input, then output should also be equal to y of n minus k. Then it is called time invariant. It is not varying with time. Even if you shift the signal, the response should also be proportionately change in the time. Then it is time invariant. Shift in equal to shift out. Otherwise, it will be time variant. For example, if a signal is multiplied by n, amplitude is multiplied by n. If you change the time, amplitude will also be changed. Right? Amplitude is changing with time. Then it is not time invariant, it is time variant. The signal is varying with time. That is time variant. The amplitude is changing with time. If any amplitude is a function of time, means it should be time variant. And causality. Causal signal. What is causal signal? Means we know the signal is zero at all negative instants of time. It is causal signal. Causal system means the system depends only on present and past inputs. Then it is called causal system. If it depends on future inputs, then it is non-causal system. So no future input needed. Right? Next, stability of the system. So stability of the system is designed with a condition called Bibo stability. Bounded input, bounded out. For a system, if you give a bounded input, bounded means in terms of amplitude. At no instant, the amplitude of the signal must be infinite. At all instants of time, the amplitude must be finite only. Then it is called bounded signal. If you give a bounded input, output should also be bounded. At no instance, output is infinite. It should be finite all instants, because we are applying a bounded input. If you apply a bounded input to a system, the output should also generate a bounded output. Then it is called stable system. That means the behavior of the signal is predictable. It should not be suddenly rise to infinite at any instance of time, irrespective of the signal. Then it is unstable signal. Right. Next, so this can also be checked with the condition called sigma h of n is less than infinite. H of n means impulse response. Y of n means just response for any input, but h of n means response of the system when we apply impulse as input. That is called impulse response. It is also output, but for impulse input. So that is represented particularly for HR, because impulse is a basic signal that used to measure as a base response of the system. Next, memory system. What is memory system means? It depends on present and as well as past values of the output or input. So it contains some past output or past input. It needs some memory or future also. It depends only on the present input. The output depends only on the present input, means it does not need any memory. So memory-less system. Otherwise, if input or output are output terms or input terms has some past values or future values, then it needs to store it, right? And so next important concept is convolution. So we have seen the systems, types of systems, right? Now, how to analyze these systems? How we can find the response of the system when a given input is applied for the system? So if it is an LTA system, the system is an LTA system, linear as well as time invariant, then its output is equal to convolution sum. convolution sum of the input with impulse response of the system. The response y of n is equal to x of n star. Star symbol is used to indicate the convolution operation. Convolution summation it is. This convolution sum indicates sigma x of k multiplied by h of n minus k. So here two signals, x of n is a sequence and h of n is another sequence, but it is input sequence, it is impulse response of the system. So x of k multiplied by h of n minus k. So what literally is going on? The signal x of n is represented as x of k. So values are not changed. X of k means instead of n we represent k. But h of n minus k means h of k is same as h of n. We are representing x of n and h of n with x of k and h of k. But h of k is modified. How it is modified? H of minus k plus n. That means h of k is changed as h of minus k first. That is folded. And it is shifted plus n. Okay. So k is varying from minus infinity to plus infinity. When k is equal to 0, h of n. So just 0. So this is sigma for the summation. We are changing k equal to x of 0, 0th sample, h of 0th sample, h of n minus. So when n is again changing with y of n, when n is changing from minus infinity to plus infinity, it's mostly from finite value. If the finite inputs are given, we'll get finite output. So that is n. But this k is how many number of samples? Right? It may be finite sample or infinite number of samples. K varies from minus infinity to plus infinity, but n varies mostly L plus m minus 1. The length of the output convolution sum must be length of the input sequence plus length of the impulse response minus 1. So if L is the length of the input sequence and m is the length of the impulse response, then convolution sum should be L plus m minus 1. So what this summation is performing means one sequence is kept constant as it is and another sequence is folded. It is folded to get h of minus k and is shifting from minus infinity to plus infinity and multiplying. So x of n is this one, h of n is this one. Will fold like this. So this is x of n. So see, this is x of n and this is h of n. Okay. So one signal kept constant, another sequence we are folding. So this is x of h of n, just we will fold it, we will reverse it, and we are shifting from minus infinite to plus infinite, and we are multiplying. Here if it is at minus infinite, product will be 0. So when we shift this folded sequence, it will be overlapped with the x of k. So for every shift it is overlapping, and when it moves beyond this one, this length, the product will be 0. Okay. That's what done by the convolution process. And this is one way of finding the output of a system, convolution system. Another way is finding the response of the system, okay, by solving the difference equation. So how will you solve the difference equation? We'll find the two responses, homogeneous response and particular response. This homogeneous response means, so any system can be represented with two responses. One is zero input response and zero state response. Zero input response means without applying any input, it may contain some output. That is called zero input response. That is called initial values. Zero state response means we are assuming that initially it does not have any output. Only when input is applied, then only it will generate output. That is zero state response. Okay? Zero input response means has some initial state. So it has some initial state. That initial state is represented with some output. But zero state response means it does not have any initial value, initial state. The initial state is 0 when switch is open. When switch is closed, the instant we are applying the input. Okay. So for example, we will take an inductor. When switch is, when we apply some supply, the input will, it has some electromagnetic magnetic field within the inductor. So if you open the switch, then also it has some energy. Now, before applying, now if I close the switch, input will be applied. When I apply the input, the response is added with the previously available response. That is zero input response. Without input also it has some because of previous state. So that is homogeneous response means zero input response. Will not consider input, will consider only previous state. And particular response means we consider all the initial states are 0.